All right, everybody, welcome back. We're going to talk about PDAs today. PDAs are the machine that correspond to context-free grammars, kind of in the same way that DFAs and NFAs correspond to regular expressions. So it turns out that CFGs and PDAs have the same power. They all describe context-free languages, and that's kind of the topic of today. Anything that is context-free is regular. As we saw before, we can do anything that's regular with a grammar, which means we can do it with a PDA. So let's go ahead and get started. These pushdown automata, the biggest difference between these and a state machine like the NFA or DFA is that they have a stack memory. Stacks are things kind of like stacks of plates. So you can put something on top, you can look at what's on top, and you can only manipulate the top. You wouldn't take a plate from the bottom of a stack of plates. You might not even be able to, right, if it's a tall enough stack. So we use that. One thing that makes this easier to use is we're going to start using deltas to indicate the end of input or the end of a stack. You can implement these things without using these deltas to represent end of input or end of a stack. But the delta does make things a little bit easier and can simplify some of our encoding a little bit. Another big difference in the PDAs is that we will use an accept and halt state. You also, again, don't have to use an accept and halt state in PDAs, but since we will be moving in that direction, we're going to do that now. And it turns out, if you look on the web for PDAs, you're going to find that there are a variety of ways that you can represent these things. We are going to use the Goddard way as opposed to the Sipser way, which is a little more flowcharty. And in some ways easier to understand. I will give you a glimpse of some ways that we can push this towards a more NFA, DFA sort of look here in a minute. But there are, I guess you would say, 5 main pieces to a PDA, or 5 main kind of states the way we're going to use it, although I might get away from calling them states. There are diamonds, which are decisions that you can be made. So when you read in an input symbol, if it's an A, you can go one direction or 2 directions. And if it's a B, you could go another direction or the same direction or multiple different directions. So reads are a decision that's being made in the tree. In some ways, you can think of them like if statements. Like, hey, if I see an A, I go this way. If I see a B, I go this way. You can also transition on empty strings, just like you could in NFA land, so that's okay. The other thing that we're going to represent as diamonds, since diamonds are decisions, are pops. So when I pop something off the stack, I can look at the symbol that I've just popped off and make a decision based on that. So if I see an X on top of the stack, then I can go one direction. Or if I see a delta, I could go a different direction. Boxes like this in flowcharts are commands to be executed. So pushes, you can't make decisions on pushes. So instead, you're just saying, I want to push this symbol on the stack. And so the only square boxes like this that we're going to have, rectangle boxes, are pushes. And then I said 5. And the reason I said 5 is I was thinking, hey, we got to start somewhere. You could list that as a bubble if you want. And then we can have an accept bubble where, hey, we accept when we hit there. You could also write in reject bubbles. We're going to tend not to do that and ignore that. So the 5 that I was thinking of are read, pops, pushes, starts, and accepts. So let's go ahead and look at one real quick and see where that takes us. All right, so here is a sample PDA. You won't be able to see the whole thing. What my image is covering here is an accept state. So I'm going to go ahead and move past the start state just a little bit, okay? And just so you can kind of see this whole picture. So what I'm really trying to show you here, and I will cut this away for a second just so that it's not bothering you, and then we'll push that back in for a second. So let's look at what's happening in this machine, right? We start up here at the top, right? That arrow leads us to a read. The read makes a decision, right? If I see a 0, in my input, I go one direction. If I see a 1, I go another direction. If I see a delta, I go another direction. So this is kind of like a multi-directional if statement. If I see a 0, I'm going to push an X. And so what you can see here is a loop that keeps occurring. Every time I see a 0, I push an X. And what I'm doing is I'm building up a stack, and I'm saving the fact that I've seen a 0. I'm remembering it, and I can remember that for as many zeros as show up. As soon as I see a 1, I'm going to pop, and as long as I popped an X off the top of the stack, I'll come over here to this read. And so what you can really think of this as is the beginning of a loop that says, hey, every time I see a 1, I'm going to pop an X. So in the first loop, I'm saving the zeros, and in the second loop, I'm remembering and matching the 1s to the zeros. And this matching is happening in a last 0 to the first 1 sort of way, and then outwards, right? So if I have 10 zeros, the last 0 in the first one, the second to last 0 in the second one, and so on, in an inner to outer way. At the end, when I get to the end of my input, I'm going to read a delta, and at that point, it's important that my stack is empty, because if my stack is empty, that means I pushed as many X's as I popped. So when you write a grammar that's like S goes to 0S1, what you're doing is you're saying, I'm going to remember the zeros so I can pop the 1s later. And that memory is what's happening in this PDA. I'm remembering the zeros so that I can pop the zeros when I get to the 1s. All right, so I want to show you one more thing just really quick. You will see other PDAs that look a little closer to what I just pushed onto the screen here in the leftish, which looks more like a state diagram. And in a sense, what you'll see is that the reads are really the states, okay? So my first read is this state here, and if I see a 0, I'm going to push X's in a loop, right? And then my second read is really this state here, and when I see 1s, I'm going to pop an X in a loop, right? There was another delta off of this read, which is if I read a delta and I can pop a delta, which I didn't draw, so technically these two don't match. But read delta, pop delta, right? Then I can go to the accept state. So what you're seeing here is a way to accept the empty string if we want to allow that. There are a couple of different ways to accept the empty string. Another way could be to change this transition to an empty string transition. Now, if you're in my class, I really don't want to see things this way. But if you're looking this thing up online, you're going to see stuff that looks closer to this. It's actually usually listed a little more complicated than this. But I think this is the format that really sells what we're doing here. You've got these two states really, right? It's the read states. And what happens are based on the input that you see and what you're capable of popping off of the stack. All right, so go ahead and pause the video for a second and look at this language down here and see if you can't write a PDA for this. I'll give you a hint. So if you don't want the hint, make sure you pause now. The hint would be what you're really doing here is you're remembering the A's so that when you see a B and a C, you can pop it, okay? So with that idea that you're remembering the A's so that you can pop them when you see a B and a C, maybe you can pause it and try it again. All right. Hopefully you're back with me now. This is what mine looks like here. And you know what? This isn't needed here. Here's what mine looks like. So I didn't make this one completely pretty, and again, you're not going to really be able to see the accept state here, but we're going to start, and when I read A's, I'm going to push X's because I'm remembering them. And every time I see a B and a C, I'm going to pop one of those X's. And this happens in a loop. I see a B and a C, a B followed by a C, then I can pop an X. And as long as I get to the end, and there are no more things to pop, and there are no more things to read, then I'll accept. And you might say, well, how do I know that this is definitely A to the I, B, C to the I? How do I know that there weren't too many A's? Well, if there were too many A's, then when I get here, I won't be able to pop delta. Instead, I'll pop an X because there will be extra X's. If there were too many BC's, then when I get to read a BC at this stage, I'll pop a delta. But if I pop a delta here, I fall off the machine and I die, so that's not good. If I get things out of order, like if I get a C here, I'll fall off of this read. If I get, I don't know, I think those are probably all the things that you think about. And then if you want to include the empty string, you can add this kind of delta here, or you could add an empty string transition over here if you do it the right way and in the right pieces. I think you need an empty... I think you need an empty string transition to... I mean, maybe just make it all the way over there, just to make sure that it works. All right, let's move on to another problem. The language of palindromes. And the hint here is partially obscured by my video, but go ahead and pause if you're ready to try the language of palindromes. If you unpause, what I will do is I will move this so you can see it completely. Right here is a grammar for palindromes, so you can see what I'm saving and not saving, right? So when you look at the grammar, I'm saving this 0, but it needs to be matched on the other side with a 0. Or I'm saving this 1, and it needs to be matched on the other side with a 1. So that kind of saving might mean that I need to save two different things. I might need to save the 0s as an X and the 1s as a Y, so that I can remember which one happened in what order later on. Okay, pause it again if that helps you. Hopefully you're back. So this is what my particular grammar looked like. So they're kind of double loops in here. What you'll see is that if I see 0s up here at this state, I'm going to push X's. And if I see 1s, I'm going to push Y's. At some point, I make the guess that I'm in the middle. And there are 3 ways that I could be at the middle. Either it's an even length string, in which case I just need to jump to the pop stage. And we can talk about that later because that's interesting. Or I make the guess that the middle is a 0 or a 1, which involves no pops, because if it's an odd length palindrome, that 0 or 1 just belongs there. And then in this state, as I read 0s, I pop X's, and as I read 1s, I pop Y's in a loop. The stack guarantees that this is doing things in an inner to outer sort of way, right? So if my input is 0, 1, 1, 0, then my read's going to push an X, and then it's going to push a Y, and then I'll take the empty string transition, I'll pop the Y, and then I'll pop the X, and then I'll read and accept this way. There are many other paths through this machine that fail. For example, read 0, push X, read 1, push Y, read 1, push Y, read 0, push X. Empty string, I can't get to the accept state because my stack has stuff on it. So there are lots of pathways when you lean on this non-determinism with the stack. There's lots of pathways that will survive, but there's only one pathway that leads me to an accept. And that's part of how popping this delta is super, super helpful in this situation. I think, the video is pushing towards 15 minutes, so I think I'll leave you kind of with another question, which is, what if you have 0 to the I, 1 to the J, but you know that I is greater than J? What do? This is very similar to something we did before, so go ahead and pause it and try it out. So here's the thing. It actually isn't really that much different than what we did before, which is on 0s we push X's, and on 1s we pop the X's. But here, instead of needing to be able to pop a delta at the end, I actually need to be able to pop an X, because I need for there to be more 0s than 1s. So I need for there to be an extra X stuck in the stack. It turns out that anything that you want to accept can be accepted with an empty stack. So this dashed box here could be deleted, and we could just go straight to the accept state here. But I drew this to show you that, look, we could just go ahead and empty out the stack and make sure that we're always popping delta at the end. That's not necessarily important for you to do in every machine that you make, but it is a neat thing to know because it can help you think about what's context-free and what isn't. All right, we're going to leave it there. If you want to try some other things, you could try a less than, perhaps, or you could try the language of matching parentheses, where you can have the parentheses that are nested and concatenated. But that's it for this time. Hope you had a good time. I'll see you all next time. Bye.